Hey guys, welcome back. We left off our conversation about ionic compounds by drawing Lewis dot diagrams to show the formation of an ionic compound, where we showed the transfer of the electrons from the metal to the nonmetal, we showed the resulting charges, and we finally found the formula. But we don't actually have to do all of that in order to predict the ionic formula for a compound. All we need to know are the charges that those ions in the compound will make in order to become stable. In other words, will the atoms gain or lose electrons to get to a full valence shell? And we can figure that out. We can predict ionic charge by looking at the periodic table and the number of valence electrons that an atom has. So these notes are going to correspond to page 2 of your unit packet. And you're going to also want your periodic table handy. Okay, so let's start off by taking a look at hydrogen. Hydrogen is in group 1 and thus has 1 valence electron. If I were to draw the Lewis dot structure for that, it would look like so. In order to get to a full valence shell, hydrogen has 2 choices, and that's a little bit unique. Let's look at the electron configuration for hydrogen. Hydrogen has a configuration of 1s1. In other words, there's 1 electron in the 1s orbital, which is of course the valence shell for hydrogen. In order to get to a full valence shell, hydrogen could gain 1 electron to make this a full 1s2. So that's one thing that hydrogen could do in order to get stable. It could gain 1 electron. And if it does, it will have a 1 minus charge. Remember, if you gain something that's negative, it's going to have a negative net charge. Hydrogen can also become stable with no electrons at all. So if hydrogen were to lose 1 electron, it would also be stable with an empty 1s orbital. That would give hydrogen a 1 plus charge. So hydrogen is unique in that respect, where it can have a 1 plus or a 1 minus ionic charge. Let's move on to helium. Helium has 2 valence electrons, 1s2. And we know that that's a full valence shell already. Even though helium is in group 8 on the periodic table, which makes it a noble gas being over there, or it's over there because it's a noble gas, I should say. The reason why it's over there is because it has a full valence shell, but it doesn't have 8 valence electrons like the other noble gases. The first energy level is full with just 2 electrons. So this element won't do anything in order to become stable because it already is. So that's not applicable to us. And helium will have no ionic charge. Let's move on to lithium. Lithium is in group 1 and has 1 valence electron. Let's look at its electron configuration. 1s, 2, 2s, 1. There's my valence electron. Now, ask yourself, what do you think is easier for lithium to do? Lose this 2s1 valence electron to become a full 1s2, like helium, to become like a noble gas? Or will it gain 7 more electrons to fill up the second energy level to get to a full 2s2, 2p6? It's a lot easier to lose just 1. So that's in fact what lithium will do. It will lose 1 electron to become like helium. And so it will always make a 1 plus charge. Also, you can just remember that metals always lose their electrons in order to get to full valence shells. Beryllium is in group 2. Here's my Lewis dot diagram for beryllium. If I were to look at the electron configuration, and I don't think I left you guys space in your packets here to do these, but that's because some people were available to learn about this and some people weren't. So For those of you that were, I do want you to take this closer look. But for those of you that were not, don't worry about it. Just simply focus on, is it easier to lose 2 or gain 6? So looking at our electron configurations, are we going to lose those 2 to get to a full valence shell like helium, or are we going to gain 6 more? That's right. Losing 2 electrons is easier than gaining 6. So we lose those 2 and we get a 2+ charge. What about for boron? Boron is in group 3. 3 valence electrons. 1, 2, 3. Is boron going to lose 3 or gain 5? Losing 3 is easier. 3+ charge. And if you wanted to look at your electron configurations for that one, 2s2, 2p1. Is it easier to lose these 3 and become like helium? Yes. Let's take a look at carbon. Carbon's in group 4. I don't know why I made these boxes so small. I hope your Lewis dots are fitting into your notes better than mine are fitting onto this screen here. All right, so now we're in an interesting position because we've got 4 valence electrons. Is it easier to lose those 4 to become like helium or gain 4 more to become like neon? Let's look at our electron configuration. 2s2, 2p2. I could lose these 4 or I could gain 4 more. Either one could happen. So carbon is kind of like hydrogen. It could lose 4 electrons, or you know what, maybe I'll write lose/gain. Could lose/gain 4 electrons. In other words, it could be a 4+ or a 4-. If it lost the 4 electrons, it would have a full 1s2, like so. If it gained 4 electrons here in that valence shell, it would end with 2s2, 2p6. And that would be your full valence shell. Let's look at nitrogen. Nitrogen's in group 5. Now here's where we're getting into the nonmetals, you guys, on the right-hand side of the periodic table. Remember, nonmetals gain electrons, but here's why. Nitrogen, with its 5 valence electrons, has a choice. Could either lose 5 valence electrons to become like helium, or gain 3 more to become like neon. Let's look at the electron configuration. 1s2, 2s2, 2p3. If we were to gain 3 more electrons, we would end with 2s2, 2p6, and become like neon. What's easier, losing 5 or gaining 3? Gain 3. And now if we gain those 3 electrons, nitrogen will have a 3- charge. Oxygen's in group 6. 6 valence electrons. Hopefully you guys are starting to see the pattern here. Ask yourself what's easier, losing 6 or just gaining 2 more to become like neon? Gaining 2. Easier than losing 6. So oxygen will always make a 2- charge. Fluorine in group 7. 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. What's easier, losing 7 or gaining 1? Fluorine and all of the other halogens will gain 1 electron and make a 1- charge. Neon is in group 8. 8 valence electrons. So as you can imagine, just like helium, it's already stable. It is not going to do anything. It will not make an ionic charge because, hello, look at these electron configurations we were trying to get to, right? 1s2, 2s2, 2p6. This electron configuration that, nitrogen and oxygen and fluorine were all trying to get to by gaining electrons is, in fact, neon's electron configuration. So neon certainly doesn't need to do anything in order to get stable. Okay, so now what I'd like you guys to do is take out, if you haven't already, I know you have your periodic tables out already, hopefully. I would like you to get a Sharpie or a marker, and I want you to label these ionic charges on your periodic tables, okay? So I'm going to scroll down here, if my mouse decides to work, to my periodic table. And I want you guys to write on your periodic tables, up above the group number, the ionic charge that those substances will always make. So, for example, group number 1, with its 1 valence electron, will always make an ionic charge of 1+. Now, I know hydrogen can also make a 1-, but for our purposes, hydrogen is going to almost always make a 1+ charge. Everybody in group 2 with their 2 valence electrons will lose those valence electrons and always make a 2+ charge. Group number 3 with their 3 valence electrons will always make a 3+. Group number 4, the carbon family, can be 4+ or 4-. Nitrogen with 5 valence electrons will gain 3 electrons and thus make a 3-. The oxygen family with its 6 valence electrons will gain 2 to become a 2-. And group number 7, the halogens, will gain 1 electron to get to 8 and thus have a 1- charge. And of course, our noble gases are not going to make ionic charges at all. Now, hopefully you're like, well, wait a second, Ms. Rivera, you just skipped over these transition metals here. Transition metals typically have 2 valence electrons. Some of them only have 1. But what's even more interesting about the transition metals is they can also donate some of their D block electrons. So, the transition metals can have various charges, but they will always be positive in nature because these are metals, and so they will lose their valence electrons. Now, how many valence electrons they lose will depend on what compound they are in. So, over your transition metals or above your transition metals, please write that they can make various positive charges. And the way that we're going to tell what the magnitude of that charge is with a Roman numeral. So hopefully you guys remember your Roman numerals. In other words, if when we are looking at our ionic compound names, and we haven't done this yet, but we will, when we look at the ionic compound names, if we were to see iron with a Roman numeral of a 2 next to it, that means that we are referring to the iron 2+ ion. Versus if we were to see iron with a Roman numeral 3 next to it, that means we are referring to the ion iron 3+. Again, these charges can be anywhere from a 1+ to a 4+. So we'll talk more about that a little bit later on in our next lecture, writing formulas and names for ionic compounds. And all we're going to need to be able to do is identify these charges and use them in order to create neutral ionic compounds. All right, I'll see you guys in our next lecture.